Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. This week on the podcast, we're featuring a series of conversations from the NIPS conference in Long Beach, California. This was my first time at NIPS and I had a great time there. I attended a bunch of talks and of course learned a ton. I organized an impromptu roundtable on building AI products, and I met a bunch of wonderful people, including some former TWiML Talk guests. I'll be sharing a bit more about my experiences at NIPS via my newsletter, which you should take a second right now to subscribe to at twimlai.com/newsletter. This week, through the end of the year, we're running a special listener appreciation contest to celebrate hitting 1 million listens on the podcast and to thank you all for being so awesome. Tweet to us using the hashtag TWiML1mil to enter. Everyone who enters is a winner, and we're giving away a bunch of cool TWiML swag and other mystery prizes. If you're not on Twitter or want more ways to enter, visit twimlai.com/twiml1mil for the full rundown. Before we dive in, I'd like to thank our friends over at Intel Nirvana for their sponsorship of this podcast and our NIPS series. While Intel was very active at NIPS with a bunch of workshops, demonstrations, and poster sessions, their big news this time was the first public viewing of the Intel Nirvana Neural Network Processor, or NNP. The goal of the NNP architecture is to provide the flexibility needed to support deep learning primitives while making the core hardware components as efficient as possible, giving neural network designers powerful tools for solving larger and more difficult problems while minimizing data movement and maximizing data reuse. To learn more about Intel's AI Products Group and the Intel Nirvana NNP, visit intelnirvana.com. And now, on to the show. All right, everyone. I am here in Long Beach, California at the NIPS conference, and I am seated with Joan Bruna, assistant professor at the Courant Institute at NYU and also at the Center of Data Science at NYU, and Michael Bronstein, who is currently on sabbatical at Harvard. Joan and Michael, welcome to This Week in Machine Learning and AI.
Thank you.
Why don't we get started by having each of you introduce yourselves and tell us a little bit about how you got involved in machine learning and artificial intelligence.
Yeah, so I did my master's and my PhD in France. And actually, at the beginning, my training was more on the signal processing and applied math. And I was not so much into machine learning up until I started to mutate during my PhD and enter machine learning through the, let's say, through the ideas and tools from signal processing. And so that was 5 years ago. And ever since, I've been getting more and more interested in ways and problems in which we can maybe leverage some of the more techniques and ways of basic mathematical tools from applied math into some of the current modern problems in deep learning. Yeah, that's kind of how I arrived here.
Awesome. And Michael?
So I did my studies in Israel at the Technion, and my main background is in geometry, so different types of geometry, metric geometry, spectral geometry, mostly in applications to computer vision and computer graphics problems. And in recent years as well, probably with like many other people, I wouldn't say everybody, basically following a little bit the hype of deep learning, we are trying to apply some of deep learning methods to geometric data, which comes with many of its challenges. There are many similarities and many dissimilarities from the more traditional Euclidean, so to say, data.
Okay. And I mentioned you were on sabbatical at Harvard. Where are you otherwise affiliated?
So otherwise, I spend most of my time between Switzerland and Israel, full professor at the University of Lugano in Switzerland, Tel Aviv University in Israel, and I also have a position as a principal engineer at Intel Perceptual Computing.
You sound like a very busy guy.
Well, don't tell to my wife.
The two of you delivered a tutorial. Was it today, right?
Yes.
You did a tutorial. Tell us a little bit about the tutorial you did.
Okay, so the tutorial is called Geometric Deep Learning on Graphs and Manifolds.
Okay.
And so in one sentence, the goal of what the tutorial is about is how can we leverage the successful techniques that the deep learning developed to process images, text, and speech into data and tasks where your input might be a bit more exotic. For example, proteins, or it could be data from a social network, or it could be data captured from let's say a Kinect, where you have a bunch of point clouds in 3D. And so what the tutorial is trying to do is to say, basically give a picture of our current understanding of how deep learning models can be used and developed in this regime, and also try to describe some of the future and current open directions.
And Michael, in your introduction, you drew one of the key distinctions here, which is Euclidean space versus other geometric spaces. Can you elaborate on that distinction?
Sure. So basically the difference between Euclidean and non-Euclidean data, one of the main differences is that you don't have the possibility of vector space operations. So in Euclidean space, you can take your sample, your point, and you can add or subtract 2 points. You cannot do the same thing on a graph, for example. You cannot add or subtract 2 vertices on a graph. So basically you have more general structures, but also less operations that you can do with these structures. So you need to reinvent many of the building blocks that basically, such as convolutions or pooling, or that are commonly used in deep learning architectures when you need to deal with these data.
So Joan, why don't you walk us through the general structure of the tutorial? How did you set the context? How did you get started?
Well, I mean, historically, yes. So there's a little clique of researchers that we started to look into this problem a few years ago, maybe like 3-4 years ago. So that was at the time where I was a postdoc in Jan LeCun's lab in New York, back at my time as a postdoc. So there and together with Arthur Slam, who is another organizer of the tutorial, we came up with a very simple, I would say, first model that was trying to set up the techniques that later on we realized, and Michael and his group also helped us understand, that they were far too naive, right? That there were a lot of things that could be improved upon this first idea. So I guess that since the very beginning, we kind of saw that there was a very interesting exchange of ideas, and also leveraging the fact that we came from slightly different backgrounds, right? Michael's group, they have a lot of expertise in geometry and understanding manifolds, and we came up with an expertise maybe where we had been working hands-on with convolutional neural networks and some of the ideas that I also worked on during my PhD that involve more the harmonic analysis of these convolutional neural networks. And so the tutorial came quite naturally. We have been also collaborating in a variety of different projects. Yeah, I mean, that's how it came up.
So for us, basically, the paper that Joan mentioned that he authored as a postdoc was actually an inspiration, and that's where we started looking into these kind of problems. So we've been working, of course, on spectral geometry for a long time, and in computer graphics geometry processing community, these or similar ideas have been around for a while, but basically combining it with learning and redefining operations, for example, in the spectral domain, as they did in their influential paper, was to some extent eye-opening, and basically we took it from there. So we wrote together a review paper that appeared in IEEE Signal Processing magazine just this summer. That for us it was also doing some homework. We discovered many works in other communities that existed for quite some time, or maybe were almost forgotten or not given sufficient attention, and maybe even in different communities people calling the same things with different names, or to some extent even I would dare to say reinventing approaches just without probably being aware of what is done in other communities. So
that never happens. What do you mean?
Well, of course it always happens, but in this domain, because it's a new field, we can probably already call it a new field or a new trend or a new niche in machine learning. And because it's new, then basically it's an effort of, there are several seeds that exist in other domains, and I think now people start getting maybe somehow a uniform picture of what exists and what's the relation between different methods. So I think the tutorial is very timely.
So you mentioned spectral analysis. When I think of that, I think of things like fast Fourier transforms and the like. How does that fit into graphs and manifolds and non-Euclidean spaces and all these things?
One way you could think about it is that it's like your dictionary, right? So
and we should probably even take a step back and explain what an FFT is for folks who might not be familiar with that.
Yeah, so maybe if we take a step sufficiently back, we can maybe start with physics, right? So there's a very fundamental equation in physics that governs how things oscillate, right? But like in a guitar or, in a domain. So like if you take, like a drum and you hit it, there's some equation that is going to determine how things are going to oscillate. And so the modes of oscillation, as you might suspect, they are related to the Fourier analysis, right? So the equation and the operator that governs this behavior is called Laplacian, right? So the Laplacian is it's a differential operator that in the Euclidean domain might look very inoffensive, right? It's just you take the partial derivatives with respect to all directions and you just sum everything. But it turns out that from this operator, you can use this as a vehicle to generalize things, right? Because now, if you want to generalize convolutions from the Euclidean domain to a non-Euclidean domain, you will have a hard time, right? Because they are defined through something that doesn't exist in another domain. But if you take one step back and they say, okay, maybe I cannot directly use the convolution, but maybe I can step back and use this Laplacian operator as a tool to maybe go from one world to the other. And as it turns out, the Laplacian is an operator that is intrinsically defined with very weak assumptions. What it means is that even on a graph or on a manifold, it's an operator that exists and it has a very complete and rich structure and status.
And the application of the Laplacian to these different domains, this is all work that was done with regard to that domain, independent of what we're trying to do here with machine learning.
Yeah, absolutely. I would not claim that I know exactly when these things, but I'm sure that many famous physicists from even like the 19th century were aware of, the existence and the generality of this operator, right? And this is why I believe that when people refer to spectral graph theory, it's most of it or a big part of it is in developing the properties of Laplacian and related operators in graphs.
As applied to graphs?
Yes.
Okay.
And so in that respect, the Fourier transform is now a concept that you can, of course, if you analyze it in the Euclidean domain, it has a very rich structure and it's useful beyond our imagination, right? It can be used to do mostly thanks to the fast Fourier transform. But it's also an object that exists in general graphs. Perhaps not with the only detail that is like a single detail, but might be very important, is that it doesn't come with a fast algorithm, right? I would say that this is one of the main technical differences.
So when I think of the Fourier transform or the FFT, I think of you have some input signal and you pass it through this Fourier transformation and it basically decomposes it into its frequency parts. How does that apply to a graph? What does that even mean?
So on a graph, basically, in the Euclidean case, you can, as you said, you can represent a function or a signal as a superposition of sines or cosines, right? Basically, some harmonic functions. So these functions turn to be eigenfunctions or eigenvectors of the Laplacian operator. In the Euclidean case, in the one-dimensional case, it's just the second-order derivative. So basically, if you replace this Euclidean Laplacian with a non-Euclidean Laplacian, with a graph Laplacian, or on a manifold, that would be what is called in differential geometry the Laplace-Beltrami operator. Basically, you get exactly the same thing. You get eigenfunctions of this operator that turn to be an orthogonal basis. Basically, it's a self-adjoint operator, so it has orthogonal eigendecomposition. The eigenvalues play a role of frequencies that are exactly, as Joan mentioned, vibration modes of basically the eigenvalues that you obtain in the Helmholtz or the spatial part of the wave equation that governs vibrations of a domain.
Joan, you were saying?
No, it's just that maybe one way where you can maybe picture this thing in your head is, if you take like a spherical plate that would correspond to a drum, as we understand it, right? It's the drum. And then you could imagine like deforming somehow the drum and just playing it. You would intrinsically, you would still be playing things that can be seen as a superposition of like fundamental waves that would look a bit more funny, right? That would probably adapt, and there would be like deformations of the original sines and cosines depending on how you have deformed the original drums.
Mm-hmm. Interesting. This is interesting stuff. It's bringing me back to my DSP class in grad school. And I don't think eigenvalues and eigenvectors has really come up much on the podcast either, but we're not going to go into the linear algebra. We'll assume a bunch of that. So basically, just to kind of to catch us up, this is all kind of background to the tutorial. Maybe let's take a moment to talk about applications of this to make it a little bit more concrete for everyone. How is some of the stuff that you're doing applied?
So maybe, we can illustrate a couple of very different applications. So one that I'm personally involved in is particle physics. Okay, so the sort of experiments that people do in a large collider, like in particle accelerators, right? Where there, the goal of the game is to say very precise things about how the standard model, like some very specific properties of the standard model. So the way it works is that you do an experiment where you clash two particles, certain, with very, very large speed, and then they produce what they call a jet. And a jet is like a shower of little events that can be detected through a very expensive and very sophisticated detector that looks like a cylinder. Mm-hmm. So, and the goal of the game is to say, well, given this observation that looks like this point cloud in my detector, how can I infer what was the underlying physical theory, right? And so it's really a and their machine learning is a very, very fundamental step for this experimental physicist. And so there, you use the techniques that we described in the tutorial to essentially learn a data-driven model that looks as input a set of like a point cloud as modeled in the colorimeter and tries to predict if it was due to theory A or theory B.
Mm-hmm. And before we go to the other application, when I visualize this, I'm visualizing, something that, is very well within the bounds of Euclidean stuff, right? It's a three-dimensional point cloud. Like, why do we need to apply the stuff that you've done as opposed to the usual stuff?
A very good question. So the answer is that you're not forced to apply what we do. So if you decide to stay in the Euclidean route, you would have to somehow quantify your measurements such that they look like a regular grid. And so with that, there are two potential risks. The first one is that if the precision that you need, if like the little blobs that the particles create are very small, you might need to sample you will need a sampling rate that will make inputs incredibly large, right? That you will basically be paying a huge price in order to transform your input into something that is in a regular grid.
Maybe another way to put that is, in order to solve this in Euclidean space, you have like a quantization noise that you have to sample more than otherwise if you were to use a different.
Correct. So there's a trade-off, right? Between so once you choose a quantization step, there's a trade-off between how large and how sparse your input is going to look like versus how much resolution you are going to lose. So in that respect, the models that we propose here, they are an alternative that don't have this limitation, right? That can stay at the native, let's say they don't lose any information because we don't need to quantize, we don't need to go into this regular grid. And I would say that there's another potential advantage is that when you look at the experiment that comes from a detector as if it was an image, right, in a regular grid, the underlying assumption is that the statistics of the input, they are following the same assumptions as the statistics of natural images, namely that everything is stationary and that there's a canonical way to compare, to measure distance between points, right? Whereas the physicists, they have a very good and sophisticated notions of how one should be comparing particles. Okay, so there's a more physics-aware version of a neural network another way to say it is that for physicists, it's very important to have a model where you can infuse and you can incorporate like prior information about how things should be compared into the model. And so the graph formulation that we are working on is allowing you to incorporate this thing into the model. Whereas if you use just a quantization and a standard convolutional neural network, it doesn't seem so easy to incorporate and to accommodate for this.
Okay. So when I go from my picture of the three-dimensional Euclidean for this application to maybe something that's a little bit less traditional, I think of like maybe looking at your points in some kind of spherical coordinate system. Is that what you're doing, or is it, because we keep coming back to graph and I'm trying to wrap my head around where graph
Yes. So here the graph enters the game as just like a data structure that you use to relate particles. Okay, so think that your input is discrete. It contains a number of particles that can be variable depending on each event. And what you learn is a network that learns how to relate and propagate information across the set of particles. And so it doesn't see it into this extrinsic Euclidean space. So of course you could say, well, it's just I can see my input as being n particles, but I can also see it as as you say, just put everything in a sphere, and then I just see it as a function, like as an image in that sphere, right? And then the notion that I have n particles completely disappears, right? And then you can connect everything with everything. I would say that it's not that there's one approach that is systematically better than the other. It's really, there's context in which you might want to use one formulation versus the other. So what I see here is that we are just providing another tool that now our practitioners can use, and maybe then they can combine with the other one. And we also have reasons to believe that in some contexts, one formulation might scale better than the other. For example, if instead of having a momenta of 4 dimensions, I had momenta of, like 8 dimensions. Well, in our case, the architectural changes to the model would be minimal, right? There's nothing in our scaling that it depends on it depends very weakly on the dimension of the input. Whereas if you had to do the quantization on the domain, you would pay a huge price for this small change.
Interesting. So you were going to give a second example?
I can give a second example, or Michael can give an example, as you prefer.
Michael, why don't you give one?
Yeah, so I can give as an example a paper that actually will be presenting tomorrow here at NIPS.
Okay.
And the example is recommender systems. So, probably the most famous example is the Netflix problem. That Netflix is a movie rental company, and they have probably tens of millions of users and probably hundreds of thousands of different movies. So the users can give different scores to movies, whether they like the movie or not, let's say on a scale between 0 and 9. So basically you can describe this information as a huge matrix that is very sparsely sampled, because of course, even if you watch continuously the movies throughout your entire lifetime, you'll probably watch just a small percentage of what they have. So they want to fill in the missing entries of this huge matrix. Basically, they try to interpolate it. And the standard approaches use algebraic techniques. Basically, you try to fit a low-dimensional model to these data, minimizing the matrix rank, or more correctly, basically the convex proxy of the rank, the so-called nuclear norm. So this problem formulation doesn't have any geometric structure. For example, you can shuffle the columns and the rows of the matrix, or if you remove one of the columns, there are infinitely many ways you can fill it in. So if you have some either side information, or you can construct it from the data, some notion of affinity between users or items, or actually both, that you can represent as a graph. For example, so think of a social network and maybe a little bit naive model that friends have similar tastes.
Right.
So this already allows you to think of the matrix as some kind of space with geometric structure. You can talk about notions like smoothness. So basically you can say that the values in this matrix vary significantly or insignificantly when you go from one vertex on the graph to another vertex on the graph. And you can actually learn optimal filters, spectral filters, for example, on this graph. Actually, it's a product of two graphs. So the best analogy from signal processing will be a two-dimensional Fourier transform, like Fourier transform of an image.
Two-dimensional, okay, two-dimensional Fourier transform.
Yeah.
Okay.
So think of the Fourier transform of an image, right? You apply Fourier transform to the columns and rows of the image. So here, instead of Euclidean structured rows and columns, you have matrix that lives on two different graphs, right? So basically the rows, for example, represent items or movies, and the columns represent users. So these are two different graphs. And you can apply filters in this frequency domain that is now basically characterized by the eigenvalues of the two operations of the rows and the column graphs. And basically this way you can have a better way of filling in the missing elements of the matrix that accounts for the similarities between different users and movies.
How specifically does the frequency domain, the Fourier transform, tie into the graph itself and in this context?
So it's very similar to what Joan described before. Basically, the spectral definition of convolution, right? You can do convolution in the spectral domain, right? The classical convolution, this is what we call the convolution theorem in signal processing, that you can implement filtering or convolution in the frequency domain just as a product, pointwise product of Fourier transforms, right? And this is what we usually do in standard signal processing because we can efficiently compute the Fourier transform using FFT. And you can do the same thing for images, right? You can do two-dimensional filters in the frequency domain. So basically extend this analogy to matrix data. Basically, you can think of it as an image, but the domains where the rows and the columns of this image live, they have graph structure instead of standard Euclidean structure.
If someone has a problem where they've got, some set or sets of entities that have some inherent structure, one relative to the other, as opposed to, some of the more traditional, image, an image or, other data types, that's an area where they could be looking at an approach like this, and it might give them some advantage.
Absolutely, yeah. So you mentioned, that a setting that is now approached and defined through different names. So now there's something that is becoming very popular recently. It's called the meta learning, right? Where it's this idea that maybe rather than using a traditional supervised learning, where I have very few number of samples and then very few number of labels, and then the environment is non-stationary, so it's changed all again and again. Maybe what I can learn is a rule that by looking at how maybe the inputs relate to each other, even if the individual distribution of the labels and the images change, maybe the underlying relationship between labels and images that I need to learn is something that I can leverage by exploring more and more data. So this is once you start setting up problems using this formulation, you end up with a task where you have to learn how to relate different things, right? Different objects. And so this is a terrain where it's very natural to look at our models. So we have a recent paper that is currently under review where we think about what's called the few-shot learning problem using this model, using graph neural networks. And so what is interesting is that somehow it generalizes and it includes as particular cases some of the models that people have been using and developing in the recent year or so to attack this problem. And so this is just to say that there are many tasks that you could imagine across AI and across sciences. The underlying thing that you need to learn is how to relate objects to each other. And so once you have to do this relational task, then a natural data structure for that is a graph or just a point cloud. So I expect that we'll see more and more applications of this technology in the near future.
So one of the things that this conversation brings to mind is a recent conversation I had, in fact, here at NIPS with Sriram Natarajan, who studies statistical relational AI. Are you familiar with that line of research and how that relates to this?
Not really.
Okay. You should check it out. Similar thinking. He's also looking at graph-based approaches and applying them to the healthcare domain and other domains. So in the case of any of the examples we've talked about, we've already talked about some of the advantages of this approach over traditional approaches. One of them is that in the case of the particle physics work, it's, maybe more intuitive for the physicist because it maps more closely to the tools and the way they're used to thinking about the domain. What are the other advantages of this approach? Are there performance advantages in terms of either computational or model accuracy or things like that?
Yeah, so what I would say that the main advantage is definitely the fact that it's more general. So there are problems in which it might be your only choice, right? That there's no Euclidean alternative to do so. But I would say that whenever you could ask the question, well, if I just forget about the grid structure of an image and just treat it as a graph, and I run my model, this model, is it going to do better than the CNN?
Right.
I would say that the answer is no.
Yeah, and that's not really the point, right?
It's not really the point, right? So I would say that the main strength of the model is really to respect the invariances that data have. For example, if you are treating if you are just observing a point cloud, you know that the order in which I give you the point cloud is completely irrelevant, right? So therefore, if you can certify that your model is going to give exactly the same output, independent of how the input are permuted, then you are kind of respecting this kind of natural invariant of the data. Okay. So I would say that relative to models that are, for example, maybe using sequential networks, like, for example, recurrent neural networks, here it could be that eventually these models based on graphs and sets are going to be more sample efficient and maybe they get you better performance. precisely because they are a bit more tailored to the data format, like to the input data format.
Maybe a good example would be applications from the domain of graphics and computer vision, and in particular analysis of deformable 3D shapes. So this is actually, I think it's a good illustration because you can treat such objects in two different ways. You can treat them as Euclidean objects, basically they are things that live in three-dimensional space, right? You can apply standard, let's say, convolutional neural networks, maybe on volumetric representations of these objects, or you can think of them intrinsically from the perspective of differential geometry, basically model them as manifolds. And what you gain in this way by resorting to these kind of architectures is you gain a deformation invariance. So basically your model is by construction invariant to inelastic deformations of the shape. And if your task, for example, is deformation invariant correspondence or deformation invariant similarity, it means that you can deal with way less training examples because you don't need to show to the network all the possible deformations that the shapes can undergo in order to learn these deformations from examples. You basically have this invariance built into the model. And the difference can be very dramatic. The difference can be in orders of magnitude, less training samples.
So, in other words, the approach you're taking to model, because it's more tailored to the problem domain, it kind of restricts your search space and you don't have to provide examples for things that wouldn't really exist in the domain itself, but do exist geometrically in Euclidean space.
Exactly. Or maybe a better way to say it is that you try to model axiomatically as much as possible or as much as makes sense in your specific problem, and everything that cannot be modeled axiomatically because, of course, there is limitation to what you can model basically in a handcrafted way. Everything that deviates from your model, you learn.
Okay. Are there other topics that you covered in the tutorial that we haven't touched on yet?
So just very briefly, so one other potential area of application that we are currently exploring, to what extent, if you now have a language to learn over graph-based structure, you can use it for combinatorial optimization problems that are naturally defined over graphs. So this is a completely different domain of application, because there the goal is not so much to solve a task that you don't know how to solve, it's more to solve or to approximate a task faster.
We're talking like traveling salesmen and these kinds of graphs.
Yes, exactly. Okay. So we briefly touched upon like one of such problems in the tutorial, which is the quadratic assignment problem. But
the what?
The quadratic assignment problem, which contains the travel state. So travel assignment problem is you can think it as a particular case of that one. So there the general setup is really an instance of this trend that you can always have this analogy between an algorithm to solve a task and a neural network. And this analogy works by looking at the algorithm and then unrolling. Typically, the algorithm involves a series of iterative steps, iterations. So you can just see these iterations as being different layers of a network. And then once you have this analogy, then you can try to study like a trade-offs between computation and accuracy, right? By just replacing the guarantees that the algorithm gives you by just a data-driven approach where you just feed the parameters of the network to a data set of solved problems. So this is an interesting and potentially also useful and because in many domains, especially when it comes to combinatorial optimization, there are problems in which it's still an open research area how to come up with efficient approximations of intractable problems, right? So here one of the potential uses of what we presented is, well, now we are providing a family of, let's say, trainable architectures that can be used to guide and to provide good trade-offs between accuracy and complexity for problems such as the travel salesman or other.
Interesting. So to paraphrase that, what you've done is your research is kind of providing a way to express graph-oriented problems in terms of neural networks. Traveling salesman, map coloring, all these other, combinatorial kind of graph problems, they're typically very difficult to solve exactly. And so there are all kinds of approximations and heuristics. But for a certain level of complexity, those don't work very well. So now your research applied to them gives you a way to solve these using neural networks.
Well, yes. So I would not
potentially.
Potentially, exactly. it's a question mark, and I think it's a question mark that it's worth exploring, right?
Sure.
That because in some applications it could be useful that, for example, to have not just have a single algorithm with a single heuristic, but to have a toggle that you can select between how much, how many cycles do you want to spend versus how much accurate do you want the solution to be, right? And be able to, to learn adaptive trade-offs and all these things are interesting. And then there's another declination of this area of research that is a bit more going into the theoretical computer science, namely to what extent the models that we learn could be interpreted as algorithms that we still don't know. It could well be that it doesn't work because it relies on this fact that can we interpret or can we uncover what the neural network is learning? And we know that this is typically a hard thing to do, right? Even for a convolutional neural network, we don't really know how the network figures out how to solve the problem. But what I'm saying is that in some contexts, it could be interesting to try to understand and analyze kind of things that the network learns.
So we have these graph problems. There are graph problems in computer science as well. Your research allows us to express those as neural networks. If we could then peer into the neural network, that might give us some insight into these computer science problems that we're trying to model in the first place.
Yes.
Interesting. Yes. How about implementation? Like I'm imagining, like at this point in time, you can't just do, TensorFlow TF dot, graph solver and do this. How does that work?
So to some extent, we are trying to leverage existing tools, not to reinvent the wheel. Basically, the underlying framework is a standard one. We use TensorFlow, for example. We just create some custom things that at the end boil down again to some standard operations like matrix multiplication.
Okay.
So basically, the short answer is yes. It
is that easy.
It is built on top of some standard frameworks.
Okay.
There are some minor but potentially profound differences in the fact that scaling up, like using these models on like large graphs or large domains involves, matrix multiplications with matrices that are large. And so the structure that we have is that these matrices are sparse. And so hopefully we see more and more integration of sparse linear algebra into PyTorch and TensorFlow, etc. But there's a fundamental difference, that maybe the hardware, like GPUs, they are excelling at a specific form of operation that is not very friendly with sparse matrix multiplication.
Okay.
So, but again, I'm not an expert in like this low-level implementation, but this, I would say, is one of the main differences between, running a ConvNet or running a graph convolution.
So you've released some code that works under TensorFlow, but it isn't necessarily amenable to scaling up just yet. There's stuff that needs to be figured out. Maybe one way to get a sense for the complexity of this, has anyone like beyond the two of you and folks that are like deep in this research use this? Are you aware of any like external arm's length applications?
So different people from different communities try to use. I wouldn't say that it's extremely popular yet, but it probably starts to become. So many different domains, many different applications the problems in these domains can be formulated using graphs. Graphs at the end are very generic and very convenient representation of any kind of relations or interactions you can think of. So that's really very generic framework of describing certain types of data. So people that are even not experts in machine learning that come from different domains that bring certain applications, they try to they see that graphs are allowed to formulate their problems in a natural way, and they are curious to try out these approaches.
Okay, great. This is really exciting stuff. Where can folks go to learn more about it? Download the TensorFlow code or read some of the papers?
So we have a dedicated website that is easy to remember. It's geometricdeeplearning.com.
Geometricdeeplearning.com. Awesome.
Where I think the idea is to have all the tutorial material. We have the review paper that Michael mentioned. We have also the recent literature by not just us, but other groups that use the tools. And then we are also going to have, in 2 months, we're going to have a IPAM workshop here in Los Angeles, where I think I'm also looking forward to it, because it's what you were saying, that people from different domains and people from different disciplines will come together and essentially present their data problem or their formulation. And what I'm expecting is that we are going to see more and more this realization that actually the models and the tools can be used across more domains than maybe we are expecting.
Okay. Awesome. Great. Well, Joan, Michael, thank you so much for taking the time to chat. I enjoyed the conversation.
Thank you very much.
All right, everyone. That's our show for today. Thanks so much for listening and for your continued feedback and support. To follow along with the NIPS series, visit twimlai.com/NIPS2017. To enter our TWiML 1mil contest, visit twimlai.com/TWiML1mil. Of course, we'd be delighted to hear from you either via a comment on the show notes page or via a tweet to @TWiMLAI or @SamCharrington. Thanks once again to Intel Nirvana for their sponsorship of this series. To learn more about the Intel Nirvana NNP and the other things Intel's been up to in the AI arena, visit intelnirvana.com. As I mentioned a few weeks back, this will be our final series of shows for the year, so take your time and take it all in and get caught up on any of the old pods you've been saving up. Happy holidays and Happy New Year. See you in 2018. And of course, thanks once again for listening, and catch you next time.